that it's okay. I think we made it far. So yesterday we were looking at this redox reaction, copper 2. Copper 2 is the oxidizer. Oxidizers take electrons, and reducers give up electrons. Another name for an oxidizer is an oxidizing agent. And S I have as stronger. And so let me write that over here. And so from the chart that we see, we're going from a stronger oxidizer, which is copper 2 plus, on the product. Now, in Chem 1B, we deal with these reversible reactions. They can go both ways. And so we look at these reactions as being a competition. The competition between the reactant mixture versus the product mixture. And if we look at the product mixture, we have tin 4 as our oxidizer. And that turns out to be a weaker oxidizer, which is tin 4. So what I mean by SOAs, I mean that's a stronger oxidizer or a stronger oxidizing agent. And WA just represents a weaker oxidizing agent or weaker oxidizer. And so this is downhill. If we go downhill in the forward direction, that's a driving force. And so it's downhill. Yeah, and so it depends on how far downhill this is. When we look at the chart, they're right next to each other. So it's not very far downhill. You know, it's just a very minor hill that we go down. That being the case, then, you know, if the entire population can make it downhill, but once the population is down at the base of the hill, some of them will go back up the hill. You know, just they might get bored. And so, in other words, what we have is we have collisions. We're going to have collisions occurring between these. And we can't stop those. And we have collisions occurring between these. We can't stop those. But the collisions occurring with these will require more energy to make it up. So that's what we're going to get. Now, the situation with this is, how much reaction are we going to get? If we go back to ammonia, this is just based on experimental data. Based on experimental data, 99.9% is unreacted, and less than 0.1% reacts or makes it up. This is a bigger hill to climb, much bigger hill. And so we could try to gauge it depending on how big the hill is to climb, but it's hard because we don't have numbers associated with that. You know? We can get the numbers thermodynamically, but what we're going to do is we're just going to look at this. So for this, we'd like to predict the stoichiometry of this reaction. That's what we want to do. We want to do stoichiometry calculations like we did in Chem 1A. And so in Chem 1A, this is what we would have done here, except I'm going to use the ICE method of stoichiometry. So we're going to use Chem 1A stoichiometry. With ICE table, ICE. Since the driving force is present, we expect reaction. Okay, so in Chem 1B, we set up all our reactions when we're dealing with stoichiometry the same. And so I'll just rewrite it here. 2 copper 2 plus plus a tin 2 plus yields 2 copper 1 pluses plus a tin 4 plus. And we set up a table like this, ICE. And what we're going to have is we're going to have 0.100 moles of copper 2 plus reacting with 0.100 moles of tin 2 plus. Initially, there's no product present, so we call that 0 moles and 0 moles here. Next, we figure out what the limiting reagent is. Which one of these is limiting reagent? Copper 2 plus is the limiting reagent. And so normally, you know, in Chem 1A, I like to do the smaller amount method. I like to predict, you know, how much product each forms. In Chem 1B, I like to do the comparison of moles method. Comparison of moles method, let's say we have 0.100 moles of tin. We need twice as much copper. So it's a 2-to-1 ratio. So comparison to moles, I'd need 0.200 moles of copper. Do I have it? I don't have 0.200, and so therefore copper 2 plus is my limiting reagent. What happens to the limiting reagent? It reacts completely. And so we're going to lose all of it. And then what we end up with is no more limiting reagent left over. How much of the excess reagent am I going to consume? 0.05, half of it. One easy way of keeping track of this is this. I use the stoichiometric coefficients here, so it's a 2-to-1 ratio. So what I say is this is going to be minus 2x, and then therefore this will be minus x. So I need to lose twice as much copper as tin, and therefore if minus 2x is equal to 0.100, then x is equal to 0.05. And so this is going to be minus 0.05 100 if I keep the same number of sig figs. And what I'm going to end up with is some excess reagent left over, unreacted. So I'm going to end up with 0.050 moles of this reactant. So when we look at the percent reaction, we have 100% reaction of the LR. But if we look at the excess reagent, how much excess reagent reacted? Yeah. We only had 50% reaction of the excess reagent. But we always base the percent reaction on the LR. And so I'm not even going to write this as 50%. Because it depends on how much initial we start off with. If we start off with 0.200, then only 25% reacted. If we start off with 0.400, then it gets smaller. Or if we start off with 0.808, the percent of the percent reaction of the excess reagent is always going to depend on how much you start off with initially, and how much you start off with there initially varies, depending on how much excess you put in there. However, the limiting reagent's always going to be consistent. The limiting reagent's always going to be 100%. And so if we ever ask for percent reaction, you always base percent reaction on the limiting reagent. We don't care about the well, sometimes, of course, we care about the excess. We want to know, are we wasting a lot? If we only react 1% of the excess reagent, maybe we're wasting. We're wasting 99%. It's kind of a waste.
How do you determine that copper is the limiting reagent?
How did I determine that copper was the limiting reagent? Usually what I do is I look at this mentally. When I do comparison of moles, this is 1. So 1 is 0.1, and therefore 2 would be 2 times 0.1, which would be 0.2. Do I have more than 0.2? Do I have 0.2? If I had 0.2, it would be stoichiometric. Do I have less than 0.2? That's how I do it in my head when I look at this. And so what I do is I look at the coefficients. Well, this is a 1, therefore this is it. And then I look at everything else because it's a lot easier. So let's say this were 3. If this were 1, then I'd say, okay, 1 is 0.1. I need 3 times as much. Therefore, it's 0.3. Do I have it? And so that's the way you'd want to do it as well. We'll do another example of that. You can see it here. All right, the stoichiometry is a 2-to-1 to 2-to-1 ratio. So how much copper plus am I going to gain? Well, if I lose 0.100, I'm going to gain 0.100 moles because conservation of mass. And so this is going to be plus 0.100 moles. And we could also use this. If this is minus 2x, this is minus x, then this is going to be plus 2x being 0.100. And this is going to be plus x. Well, X is 0.0500, so this has got to be plus 0.0500 based on the stoichiometric ratios. And so at the end of this, I'm going to form, this is my theoretical yield. The theoretical yield of copper plus 1 is 0.100 moles, and the theoretical yield of tin 4 is 0.0500 moles, or 0.050. Just do 0.0500 moles to keep the sig fig square. And so in Chem 1A, it either has a driving force or there's no driving force. If there's a driving force, we assume complete reaction. If there's no driving force, we assume zero reaction. So if there's a driving force, we assume 100% reaction. If there's no driving force, we assume 0% reaction. But are things so black and white? It turns out, no, things aren't so black and white because, you know, it's like the hill climb. So we'll make it back up the hill. And so this turns out to be wrong. And so we're going to have to use Chem 1B stoichiometry for this. Well, what is Chem 1B stoichiometry? What is that? You know, and so this is it. It didn't work. So one thing we could do is we could just approach this theoretically. You know, theoretically, could be like this thing I was talking about earlier. You know, the hill, whatever else is going downhill, uphill. In Chem 1A works because most of the reactions we look at in Chem 1A, the hills are so huge. So for example, if we go downhill, it's like a huge precipitous drop. We're dropping off a gigantic cliff. And so everybody can make it down to the bottom of the cliff, but can you make it back up? And so even the most energetic species down here don't have enough energy to make it all the way back up the hill. And so in that case, we're going to have 100% reaction. Or the opposite, you know, the hill is so steep and so tall that nobody can make it to the top. That's 0% reaction. In Chem 1B, we have a hill that's not so big that we can have things occur both ways. So in Chem 1A, it still works. We do stoichiometry, but we're selective about the reactions that we do. The reactions that we do in Chem 1A are like sodium hydroxide plus HCl. You know, sodium hydroxide plus HCl, that's a huge hill to go down. Everybody goes down, nobody makes it back up, pretty much. Or negligible. Maybe once in a while, a random one would make it back up, but nothing that you could measure. But when we have this, and we know that this hill is not so big, because when we went back and looked at the redox chart, when we went back and looked at the redox chart, they're right next to each other. I had to go to Appendix D for this because the redox chart there is not comprehensive enough. And Appendix D is a much more comprehensive redox chart. A lot of data in Appendix D. Oops, page down. In our redox chart, over there in the classroom, we have this top one, copper 2 plus 2 electrons yields copper. And all these species here are gaining electrons. Any species that gains electrons is called an oxidizer. And usually what I remember is, okay, which way is stronger? Is going up stronger or going down stronger? And the way I remember it is, it depends on where fluorine is located. Where is fluorine located on this chart? At the very top, so that's stronger. But this chart has this one. This copper 2 goes to copper plus 1. This is the one we want. Okay. And we're comparing the strength of copper 2 plus, which is the oxidizer on the reactant side, versus tin 4 plus, which is the oxidizer on the product side. And is there a huge difference in the strength? No, they're right next to each other. And so they're kind of, if they're comparable, is it going to be a one-way? You know, they're both fighting for electrons. Is there going to be a clear winner here? It looks like copper 2 plus should be, but how much stronger is it? Just a little bit stronger. And so it's not, whereas in Chem 1A, we'd make sure that there's a huge difference, you know, and then we can just use regular Chem 1A stoichiometry. And so this is definitely not going to be a one-way reaction. And so how do we deal with this, is the question. And so this is like, okay, you have a problem here. And the problem is we want to figure out what the stoichiometry of this is, yet we don't have any tools to do that. And so the tools would be Chem 1B stoichiometry, but what are the tools of Chem 1B stoichiometry? Well, of course, somebody's already figured it out, but what we're going to do is we're going to try to figure it out ourselves. We're going to try to figure it out ourselves because this is how, you know, most science works. Most of the time, you do your day-to-day grind in the laboratory, and what you're doing is you're taking lots of what? Typically, when people go in the laboratory, they're taking lots of data. The data, experimental data from experimental observation. You do. And so what we're going to do is we're going to take some experimental data, the observations, and then just take a look. So rather than trying to figure this out, we're going to go into the laboratory and we're going to just mix it together and see what happens. We mix it together and see what happens. Maybe we'll see what? Maybe we'll see some kind of pattern. And if we see some kind of pattern, then maybe we can use that pattern to make predictions, especially if that pattern is very consistent, because if that pattern is very consistent, you know what the most concise definition of a pattern is? The most concise definition of a pattern is a mathematical equation. If you can define something by a mathematical equation, you know there are no words. It's just a mathematical equation. It's a very simple, concise definition. It's like the ideal gas law. Do you want to explain to somebody in paragraphs or pages, you know, how a gas behaves? An ideal gas behaves? No, it's much easier to just say, oh, PV equals nRT, and that pretty much defines how the ideal gas behaves. You know? And so if we can come up with some kind of law, that would be even better, you know, because that would be a reliable pattern. A law is a reliable pattern. However, a rule is not necessarily a reliable pattern, you know. When I think of laws versus rules, you know, I think of two different levels. Rules are going to have lots of exceptions, whereas laws should have, you know, hopefully zero exceptions or minimal exceptions. There are going to be exceptions in laws because, like the ideal gas law, does the ideal gas law work for everything? No. So sometimes we have to modify it to make it work. But for the most part, you know, under certain conditions, the ideal gas law works quite well. If you go to more extreme conditions, then it doesn't work so great. But anyway, whereas rules, you know, like solubility rules, somebody asked me, you know, what solubility rules they should try to remember. And so if you see the tutor here, you know, the chem tutor here is quite good. His name's June. He's been tutoring here for many, many years. He does a lot of private tutoring as well, but he has a set of solubility rules that are different than the ones I use, but it doesn't matter which set you use. It's okay. I mean, they're close. The solubility rules varies from book to book depending on how many exceptions you want to deal with, you know, and that kind of stuff. Do you guys remember the solubility rules? It's a useful thing to remember. So that was wrong. So what we're going to do is we're just going to go back and just take some observations. The observations are what we call factual data, you know. Versus we can come up with some kind of hypotheses, you know. And whatever hypothesis we come up with, the hypothesis must agree with factual data. And the factual data is observations. So you can come up with some kind of hypotheses, and if it doesn't agree with facts, then the hypothesis is wrong. You know? And if the hypothesis makes it to a theory, you know, hypothesis is your first tentative. If we understood the theory, you know, like this, the theory of the chemistry that's happening here, then we should be able to predict where it's going to end up. It doesn't end up here, it ends up somewhere else, and we should be able to predict that. Because if we understood the theory, we'd have a good fundamental picture of what's going on, you know. Maybe there's 100 bicyclists at the bottom, and only 3 make it to the top, you know, because I understand the theory. Other than that, there are only 3% of them make it. Something like that. But we're not going to approach it that way because we don't have... Do you have the theory of chemistry pretty well mastered? What is the theory that we use to describe chemistry? Quantum mechanics is the theory. Are you pretty good? Are you quantum mechanics master? No. What's that?
Coulomb's law.
Coulomb's law, yeah. Coulomb's law, but Coulomb's law is a good first approximation. Quantum mechanics deals with the plus and minus, but you know we got to look at the shapes of the charges and charge density and this kind of stuff. The orbitals, all that stuff has to be factored in, and so quantum's used. But we aren't. So what we're going to do is we're going to try to approach this from the traditional method. We start off with observations. We look for patterns. Well, hopefully those patterns will tell us something about the Chem 1B stoichiometry. So we'll take some observations here. These observations, you know, when we take observations, it's a lot of work because we have to do experiments. And so experiment 1 here is going to be 2 copper 2 plus a tin 2 plus goes to 2 copper plus 1s plus a tin 4 plus. And so the first one is, let's start off initially at the same conditions, 0.100 molar and 0.100 molar. And then rather than try to predict what's going to happen, we're just going to, well, molar, it's not molar, it's moles, sorry. I'm jumping around a little bit. Okay, now it's okay. We'll go 0.100 moles, 0.100 moles, 0 moles. I'm not going to do grams because I don't want to do gram to mole conversion. I'm just going to do moles to keep the stoichiometry simple. And so what we're going to do is we're going to put this in here and mix these chemicals together and give them plenty of time to react. So that by the end of this, there's no further change. So we just wait until there's no further change and then see what happened. And so let me grab the data here. Grab the data off this. Oops. I close the page. Let me grab the data here. this is where it ends up. So we're going to have, at the end of this, which is equilibrium, or the end, 0.03, 36, 68, 64, 32. 36, 68. Actually, all I need is this one. And so did 100% of the limiting reagent react? No. What percentage of the limiting reagent reacted? So if I started off with 100 parts and I end up with 36, then that means I lost how many parts? 64. And so 64 out of 100 is what percentage? 64%. So the max I got is 64% reaction for the LR. And so in Chem 1A, we would have predicted 100% reaction. Here we only got 64% reaction. But you know, there are other numbers, which I already forgot. But you know what? Even in Chem 1B stoichiometry, conservation of matter holds. Whether it's Chem 1A, obviously conservation of matter holds, right? And so if I lose 0.064 of the copper, how much of the tin did I lose? Yeah, 0.032. I must have lost 0.032 of the tin. Because the way I can visualize this is minus 2x, and this is going to be minus x. So if 2x is 64, then half of that is 32. And that means only 32% of the tin reacted, but that's an excess reagent, so that varies, you know. But the limiting reagent, that should always be consistent, 64%. And so how much tin do I have left over? Yeah, I'm going to have 0.068. Is that all right? 0.068 moles. So I forgot the number, but let's verify that. I'm going to verify that here. And yeah, we now end up, they measured a 4 sig fig, so I'm just going to go 3 decimal places since, you know, addition or subtraction. But this is it. I guess I could go 4 sig figs because this comes from experimental data. This doesn't come from the subtraction, so this would be correct. So maybe I'm going to add an extra 0 there. But I have 68 left. So, and then I get 64 and 32. So let's see if that pans out the same here. So I'm going to add the extra 0 here because this actually came from measurement. So they went in and measured how much copper 2 was. And they went in here and measured how much tin 2. And then if I lose this, then stoichiometry tells me that this is going to be minus 2x for the copper, and this is going to be plus 2x on the product side. And we already know what 2x is plus 0.064. So this is going to be plus 0.064 moles. So if I start off at 0 moles, and then I add 0.064 moles, then I'm going to end up with 0.064 moles. And then this is going to be plus x, because the stoichiometric ratios have to hold. It's a 2 to 1 to 2 to 1 ratio. And so we know that this is going to be plus 0.032. And then we end up with 0.032. But again, these came from measurements, not my calculations here. So I need to add that extra 0. Because their equipment can measure 3 sig figs. And so that gives me 640 and 320. Is that what they observed? Yeah. Actually, let's double check to make sure. So coming from experiment, yeah, they got 640 and 320. So that's what they observed here. But you know, in order to do these calculations, we would have had to know the first one at least, you know, or all of them. It's best to measure all of them just to make sure. All right, that's easy. 64% reaction. Do you see that? Seems to be okay. I'll leave a little space here to analyze it. So what we're going to do is we're going to do this. We're going to go to experiment 2, and this is a reversible reaction. So what it, you know, to me, the one way of visualizing this is if you have 100, you know, initially at the top of the hill, then all 100 can make it to the bottom, but maybe 36% of them will go back up. And that's it. And I'm thinking of this being the top and this being the bottom because more, you know, the driving force is forward. And so there's more forward reaction here. So let's, what we're going to do is we're going to put everybody at the bottom of the hill in experiment 2. So we're going to start off with 2 copper 2 plus a tin 2 plus. This is going to yield 2 copper plus 1s and a tin 4 plus. And so I'll set up my ice table, but initially there's nobody at the top of the hill. So this is 0 moles and 0 moles. And then we're going to put everybody at the bottom of the hill, 0.100 moles and 0.100 moles. So if everybody's at the bottom of the hill, how many do you predict are going to go up to the top of the hill? 36%, I'd predict, because 36% can make it. If 36%, we're going to take 36% of the limiting reagent. So Ashley, how would I figure out which is the limiting reagent going backwards? Because now this is a two-way reaction, so some can go backwards, go up the hill like this. And so looking at this, what would you do? We are going to do comparison of moles method. Comparison of moles method, you look at the coefficients. This is a 2, this is a 1. So what you would do is you go to the 1 and call that, okay, if this is 0.1, then 2 means I need twice as much. So if this is 1 at 0.1, then 2 means I need 0.200. And do I have it? No, I have less. And so this is my limiting reagent going backwards. So the limiting reagent, we want to know how much of the limiting reagent should make it back up the hill. I suspect, you know, this is our prediction. I'm going to write this as a prediction based on our observation. You know, we want to make, I see a pattern there, and the pattern is we had 36% reaction, correct? And so my prediction is I'm going to get 36% of these making it up back the hill. And so this should be 0.036 moles. And that means how many are going to remain at the bottom? I'm going to have, out of my limiting reagent, I'm going to have 0.064 moles. Does that sound right? Okay, now I'm going to fill in the rest of it based on stoichiometry, the mole ratios here. So the way I do that is I do it like this. This is going to be called minus 2x. And therefore, how much tin do I predict to lose? Minus x. Because copper is going to react twice as much than the tin, so I'm going to react half as much tin. So for every 2 coppers, I need just 1 tin. For every 1 tin, I need 2 coppers. So over here, it's going to be what? Well, half of 36 is what? 18? Is that right? So, so the first one, the initial is we're expecting 36% here. Expected. And so this will be minus 0.018 moles. And 100 minus 18 is going to be 0.82 moles. Okay. And then how much tin 2 will I gain? Yeah, this is plus x, so I'm going to gain plus 0.018 moles, and 0 plus 0.018 is just going to give me 0.018 moles. I start off with nothing here. And then over at the copper, I expect to get 2x worth, and 2x is 0.036, so I expect to go plus 0.036 moles here, and this should give me 0 plus 0.036 is just 0.036 moles. So these are my predicted values. So in terms of the scientific method, we don't have to understand the theory. So for example, to use the ideal gas law, do you need to know everything about the theory of gases? No, you don't need to know anything about the theory of the gases, but you can make lots of predictions using the ideal gas law. And so, we don't need to know the theoretical basis of this. We just want to use patterns to make predictions. And so what we're going to do is we're going to use the pattern from experiment 1 to make a prediction here. Okay, of course, what we want to do next is we want to test the prediction. We want to make sure the prediction is accurate. And so that's going to require experimental work. And so if we actually conduct the experiment, so what we're going to do is we're going to mix the copper plus 1 and the tin 4, and then just wait until it reacts completely. Once it reacts completely, then we take a look and see what we end up with. And so from experiment, remember, experiment is fact. Our prediction may be accurate or may not be accurate. If our prediction disagrees with experiment, then experiment wins and our prediction fails. And so let's take a look at the numbers here. And so I have the numbers here. So for the copper 2 plus, we get 0.0567. Or moles. Is that close enough? So our prediction, we got it like 0.036, 36. We end up with 57. Is that close enough? Seems kind of far off. So that means the experiment failed? Maybe. And so what we need is we need reproducibility in experiments. And so, that's important in science. You have to be able to reproduce the results. Sometimes experiments do fail, and so therefore you shouldn't call all of them fact. Sometimes they're mistakes made. So sometimes there's controversial results that come out, and those controversial results people try to repeat and then see if they're reproducible. Sometimes those results are reproducible, and then they have to modify their understanding of things. Other times it was a mistake. But in this case, let's say this was repeatedly done over and over, and the averages the data all came out close to 0.0567, plus or minus. There's always going to be fluctuations. You know what those fluctuations we call? Just these fluctuations in the data. Like, for example, let's say somebody got, rather than 567, they got 566. Then all of a sudden, are you going to say there's a large error? No, there's these fluctuations which we call, what type of error? Systematic error or random error? Those are called random error. We also have to make sure there's no systematic errors too, make sure everything's calibrated properly and that kind of stuff. So let's say there's no systematic error. Systematic error we can get rid of easily. Do you know how we usually get rid of random error? There's an easy way to get rid of, well, not so easy because, in theory it's a very easy way to get rid of random error. Yeah, doing multiple trials. In theory, if you do an infinite number of trials, then half of them will be too high, the other half will be too low. Actually, I shouldn't say half, because some will be right on. And what we can do is we can average out those. But normally we don't do an infinite number of experiments. We do a finite number of experiments. So the more experiments you do, the more you can average it out. And so the way we get rid of random error, or we can't get rid of it completely because we'd have to take an infinite number of experiments, but we can try to minimize the amount of random error by doing multiple trials and averaging out the random error. So some are going to fluctuate high, some are going to fluctuate low. You average it and you try to minimize the random error there. And so let's say that's already been done. So this has already been done, and so this is a reliable result. This reliable result is going to be factual now. And so when we look at this, our prediction's way off. You see that? In fact, if I know I form 0.0567 moles, since I don't want to jump back and forth, here I can make a prediction. This prediction should be accurate, because if I know I form 0.0567 moles and that number has been minimized as far as random is, and we have zero systematic error. Random error in theory cannot be completely eliminated. That's kind of weird, and that comes from quantum mechanics. There's a fundamental limit to it. But going back to this, if we are left with 0.0567, or not left with, if 0.0567 moles of copper 2 form, how many moles of tin 2 formed?
0.284.
Well, I'll just not round it. I'll call it 3.5 moles. 0.02835 moles. I'll round it later. And then that means we lost how much copper 1? Okay, that's how much we have left over, right? 0.0433 moles. And the tin 4, how much do we have left over? Here we can round it if you want. It's going to be 284. So 100 minus 28.4. 0.0716. Okay. Actually, I'll make this not subscriptive moles. So that we can predict if the first number is accurate. Let's see what the data showed us. And so this is what we call like rounding error, but we'll talk about that later. So we can round this. What was it? 2835. We should have rounded that to 284, but that's based on this number. These numbers actually come from experiment, and so these are the actual measurements. So ours just came from the calculation, and so looking at the experiments, this is the experimental data they got here. And when I look at this, I had 64% reaction here, and I was expecting 36% reaction in the reverse, but what did I actually get? So this is the actual. And so I actually got yeah, 57 or 56.7% reaction. So do you think do you see a pattern there in percent reactions that you can use? No. I mean, 64 and then 56.7, I really don't see a pattern there, do you? No. So we got to look for some other pattern in the numbers. So one of the things that we try to do is this. We try to just, if you don't see a pattern now, maybe what we need is more observations, right? The more observations, maybe the patterns will become more apparent. And so we'll go on to the next. Oh, was there a question? No. All right, in this experiment 3, what we're going to do is we're just going to have 0.100 moles of everything. So we're going to start off with equal numbers at the top and at the bottom of the hill, and then see which way it goes. And so when we look at the other patterns, if we look at the first one, there was a driving force for the forward direction. So we had 64% reaction because it seemed like, the forward reaction was favorable in the first one. We go to the second one, and we get more than 50% going in the reverse. If we have more than 50% going in the reverse, then it appears that the reverse is favorable. So which one is favorable? Is the forward reaction favorable, or is the reverse reaction favorable? That's going to tell us the downhill direction. So it's a little bit confusing, isn't it? Maybe what's wrong is my fundamental description of what's going on with the bicyclist is totally wrong, Maybe that needs to be fixed. So we go here, and which one do you predict? Should it go forward or should it go reverse? Which way is favorable? In terms of thermodynamics, the forward is reversible. Because when we're going from stronger to weaker, that stronger to weaker is in terms of chemical potential energy. And so when we're going from stronger to weaker chemical potential energy, that's downhill. So actually the downhill direction is forward. But I don't know anymore because what happened in the second reaction 2, something weird is going on. But anyway, what would you predict? Well, maybe it's a 50-50. Maybe it goes forward, maybe it goes reverse. I don't know, but what we're going to say is, I don't even want to guess. What we're going to do is we're just going to do this experimentally and then see where it ends up. And so let's go ahead and see where it ends up here. So this is experiment 3. So we're going to have 0.0922 at the end of this, which means we lost how much? Okay, 7.8%. All right, so it's going to be minus 0.078. Or actually, let me go with more sig figs here, because they give us 3 sig figs for the measurement here. I have it in my pens.
It's 0.00.
Yeah, sorry, 0.00. Is it? Yep. I don't know what's so wrong with the word, but it crashes a lot on me. It's when you got these new computers. These new computers have even more RAM. This is an HP computer. This HP computer I got from school. The first thing I did when I got this HP, it came with 8 gigabytes of RAM. I went out and bought some more RAM, so I have 16 gigabytes of RAM in this. But this HP is giving me lots of problems with Word crashing continuously. My Word is gone. So anyway, I'm going to go to Excel here. But my Excel has crashed. So there's something wrong with this. Camtasia recorder is very high. But I'm not using a whole lot of memory here. 44% though. Maybe that's too much. I'm going to close Acrobat. Close Edge. Let's try Word again. The latest version of Word? Yes, I do. I have the Microsoft Office 365, so it periodically updates everything. Let's save this. Let's call it. Let me rewrite that really quick. 2 coppers plus tin 2. 2 copper 1s plus tin 4 plus. Change, we don't know. We'll just see what we ended up with. What was the number? 0.0564? 0.0522? 29? Oh, let's see. Oh, yeah, it was a very small number. It was 0.0922. Oh, actually, it's a very small change is what I meant. And what's the change here? Minus 0.00778? 78. Okay, thanks. So if I know this, then I can figure out the rest because I lose half as much of the tin. So this is going to be minus 0.0039. And so what is that going to give me left over? This is going to give me 0.0961. And then I'm going to gain plus 0.0078 over here. Conservation of matter. And so this is going to give me 0.107. Now, here I'm going to just carry the extra digit. I'm almost not allowed that, but and then this is going to be plus 0.0039 moles, and that's going to give me 0.1039 moles. So it did go in the forward direction. So the forward direction, well, kind of what we were suspecting, should be the downhill direction. But the reaction number 2 is strange.
So, like, what's this experiment? Like, is it that you have a system with all of these ions in there, and then the ones on the left react with each other and form more of the ions that are in there?
So the first thing is, what was the percent reaction here of the limiting reagent? 7.8%. And so this just further shows we can't use percent reaction, right, as our pattern. We have to come up with some other pattern. And so can you look at these numbers and tell me what the pattern is? Just look at these numbers here, 922, 961, 1078, 1039. And we could look at the pattern of the other numbers here. This is from our book. So, so from reaction 1, the pattern of the numbers is 36, 68, 64, 32. So remember that. Experiment 2, the pattern was 56.7, 28.3, 43.3, 71.7. Remember that. And from reaction 3, we have 92.2, 96.1, 10.78, 10.39. Or 103, I should say 107.8, 103.9. You know. So those are the patterns. Do you see a pattern there? Because what we're looking for ideally is a mathematical pattern. You know, if we can find a mathematical pattern there, then do you think there's a mathematical pattern, or is this totally random? You know, each time you mix these together, yeah, well, ignore that pattern. There is a pattern there, but the thing is, I'm trying to show what scientists do in using the scientific method. So we got to come up with a pattern here. Now, if you're actually, there's a talk. Do you know this person here? Terrence Tao? Of course, yeah. Is everybody familiar with this guy? Some like genius mathematician, apparently, or something, highest IQ or whatever. Well, maybe he could look at those numbers and tell me what the pattern is. Could you look at those numbers and tell me what the pattern is? Me too. If I look at those numbers, it just looks like a jumbled mess, doesn't it? A complete mess. Well, actually, this person's giving a talk, live streaming via Zoom, Thursday, this Thursday at 6 p.m. So I registered for it. Maybe I'll just watch it and see. Obviously, it's a math, so I'm not very good at math, and therefore I probably won't understand any of it, but it'll be interesting to hear, because I've never heard his current research or what he's doing. But if you're interested in this link, I could send it out. I don't know if anybody's interested or has time to watch, but I'm going to check it out. This is UCLA. You could have gone in person for the talk, but it's too far away. And so what we're going to do is we're going to try to figure out the pattern for this. One of the things that we do in figuring out patterns is this. We try to graph it. I don't like this. They show what the pattern is, but you know, try to derive it. And so since I didn't, okay, let me do this. Okay, that's from reaction 1. So let's try to graph this one here. And when we're looking at the numbers, this is a process called data reduction. Data reduction is you have lots of numbers there. It's hard to see the patterns. So what we try to do is we try to reduce it rather than having a whole bunch of jumbled up numbers. We try to see if there's some kind of thing we can look at. And one of the first things, I don't know what, I tried the pattern. The pattern was percent reaction. Did my pattern work or fail? It failed. So I'm going to just go at random and try to figure out some other stuff. So if you recall, this one, we started off with 0.100 molar copper 2+. So that'll be my 0.100 molar copper 2+. And we started off with 0.100 molar tin 2. So that will be my tin 2. And what this is going to be is, over here, this is going to be the amount in moles on the y-axis. And over here on the x-axis, I'm going to put time. So over time, the copper 2 reacts. Which one reacts faster, the copper 2 or the tin? The copper 2. So the copper 2 reacts faster than the tin, and eventually we're going to bottom out at 0.036. So this is going to stop. I should have made it a little bit deeper, but it's all right. We're going to lose about 2/3 of it. We're going to have about 2/3 left. Now, tin is going to react slower. I don't know if it reacts linearly or non-linear. That is, this is a topic. We need more measurements. Does it go as a straight line or does it curve? Curve would be non-linear. Straight line would be linear. I'm just guessing here. But you probably can see that they already put it as non-linear. All right, I'm going to consume half as much tin. So it's going to drop down and then, oops. Let me redo this line here. It's reacting slower. And then I end up at 0.068. This would be moles. Okay, so what happens here is there's going to be a point in time where nothing changes anymore. And that's going to be when we hit the end of the reaction, or equilibrium. Before we do that, initially what we're going to have is we're going to have forward reaction occur. And what happens is, all we have is product. We have zero reactant. All we have is reactant. We have zero product. And the product I'm going to write down here. The product is going to be copper 1. And I'm going to write a squiggly line for that. And tin 4. So initially, we just have forward reaction occur. And then what is going to happen is the reactants, we're going to end up with 0.064, as the reactants react, product starts to form. The product's going to grow until we hit the end of this. At the end of this, I'm going to end up with .064, and then the tin 4 is going to increase until I get to 0.032. So initially, we only have forward reaction. But as we start to build up some product, then the reverse reaction can start to occur. So we mainly have forward reaction here, but we have a little bit of reverse reaction occurring. And the more and more product, the higher the concentration or the higher the amounts of product, the more those collisions can occur. So we're going to start building it up. And by the time we hit the end of this, then the forward reaction and the reverse reaction rates are equal. In other words, the collisions become so frequent that they equal the forward reaction. The collisions, the successful collisions that cause reaction will equal it. And so here we've reached a state of equilibrium. Under equilibrium, the amounts don't change. However, this is called a dynamic equilibrium. Why is it called dynamic? Means change. Equilibrium means no change. So we have change but no change. And so the no change part, the amounts stay fixed. The dynamic part is that there are going to be particles going up and down the hill, and that doesn't stop. But for every 3 particles that go downhill, 3 particles will go uphill. And so there's no net change. But you can't stop the collisions. The collisions are going to occur regardless. You can stop the collisions if you drop the temperature to what? Temperature? 0 Kelvin, but we're not going to do that. So the collisions never stop. Okay, now we see a pattern. And so we look for any kind of pattern. My pattern is going to be magenta, solid, blue squiggly, blue solid, magenta squiggly. Do you see that pattern there? So maybe that pattern holds in the second experiment. And so let's take a look at the numbers for the second experiment.
So for the copper plus, what made you decide that it's linear, or is that supposed to be linear?
No, I don't know if it's linear or non-linear. So we'll put a question mark there. All we do is we look at the data and see what the experiment is. We'd have to look at the data to determine that, and then when we look at the data, which is here, I ran out of colors there because of adding color palettes, so I'm just doing this differently than this, but we're just looking for patterns here. How much time do we have? 15 minutes. Okay, maybe I'll just use their patterns here. But anyway, this looks nonlinear to me, just slightly nonlinear. That comes from experimental data, and so into that. And normally, nonlinear processes are quite common. When when you have lots, then it reacts fast. But as the amount dwindles and gets smaller, then things start to slow down. The same thing with heat. If it's super hot, then the heat transfer is very quick, but as it gets closer and closer to room temperature, then the heat transfer is very slow. So that's a case where it's nonlinear. Right? And so typically this is nonlinear, but not always. We don't know. I mean, that's just a prediction. And if that prediction holds 100%, we could call it the law of nonlinear, and then make that prediction. We do that. But in an effort to save time, we do the same thing for experiment 2 and experiment 3 and see if we have a pattern. So I did squiggly and whatever else. But here, we're going to do it this way. Blue, black, magenta, green. Okay, fine. Then we go over here. Do we see the same pattern? No, but is it inverted? Yeah, it's inverted here. Blue, black, magenta, green. It's inverted, but look at the spacing. Do we see a pattern in the spacings? So we look at this. This is called graphical analysis. We're just trying to reduce the data into a visual representation of it and see if we can see a pattern. And then we go over here, and then what's the pattern? Green, black, blue, magenta, and that throws everything off, right? Or do you see a pattern? Maybe Terrence would see a pattern here. Do you see a pattern? I don't see a pattern here. Maybe if my, I don't see a pattern. Probably Terrence could probably see a pattern there, save some time. Or AI, maybe AI could see a pattern there. Throw it into ChatGPT and see if ChatGPT can determine the pattern of the numbers, right? Probably. So you got to. All right. So what we're going to do is maybe with the spacings and this type of stuff, we don't see a pattern there, and so we try other mathematical representations of the data. So we try to reduce this in different ways. So one way of reducing the data is by graphing it. Another way is seeing if this fits some kind of mathematical pattern here. And so one of the mathematical patterns might be not percent reaction, maybe it's the ratio. Maybe, we come up with the same ratio of products to reactants. So we'll try another pattern. This pattern didn't work. At least, maybe it works, but I just don't see it. And sometimes seeing the pattern, sometimes I'm blind. I don't see it, but the pattern's there, and somebody else sees it right away. Not just physical scientists do this, but also social scientists, because I was listening to a TED Talk, and this very famous social psychologist, I can't remember her name though, she's from Texas, and she has a bunch of TED Talks on there. But she was talking about how she tries to look for patterns in human behavior. And so she takes lots of observations and then collects these observations on sheets of paper and then she throws all the sheets of paper on her living room floor or something, pulls up a chair, and then just stares at it. Just stares at them until the patterns come out. And so maybe it's not enough time. If you were to stare at these numbers, eventually, would you see the pattern come out? Well, we could stare at this, but we're going to take a little bit more action here. And one of the actions is we're going to try ratio. Maybe we'll do a product to reactant ratio or something like that. And so in this ratio, what I'm going to do is I'm going to take maybe the products and not add them together. I might just try to multiply them together. I could try adding them together too, but I'm not. I'll just do 0.064 times 0.032. So this is my product moles, and then I'm going to divide it by the reactant moles here, which is 0.036 and 0.068. 0.036 and 0.068. I would have tried everything. I'd try, multiplying these, I'd try adding them, I'd try all different kinds of things to see if I can get some kind of mathematical pattern to fit that data. If graphing worked, it's easy. If the graph worked, then we can define the graph using lines or whatever else, and then have the computer come up with an equation for that. Okay, so what does this ratio come out to? And so let's try this here. 0.064 times 32 times 0.032 divided by 0.036 divided by 0.068. And I get 0.8366. Okay, that's from experiment 1. From experiment 2, we'll try the numbers here from experiment 2. $433, 717. 433.0717. And then the reactants were 567 and 283. 0.0567 and 0.0283. And so 0.0433 times 0.0717 divided by 0.0567 divided by 0.0283. And I get 1.934. So based on these numbers, can you predict experiment 3? No, I don't know. It just seems kind of random. But let's go ahead and calculate experiment 3 and see what it comes out to. So experiment 3 was 1078 and 1039 on the top. So 0.1078 times 0.1039. And the reactants were 922 and 961. So 0.0922 and 0.0961. Let's see what that comes out to. So 0.1078 times 0.1039 divided by 0.0922 divided by 0.0961. It's 1.26. Would you have been able to predict that? 1264 based on the number pattern here? No, I wouldn't have been able to predict this at all. And so I could try different things. Maybe not the product to reactant, products on top of reactant. I can flip it over, but if I flip it over, then there's still no pattern. I could try adding it. You know, all we're doing here is, of course, what we want to do, if we knew more about the theory and that kind of stuff, it would help us. But right now, we don't know what it is, and we don't know what the mathematical equation is, so it's just guessing. So it doesn't really matter what you guess. And so one thing is the stoichiometry. You know, I have to remember the stoichiometry says there's twice as much copper as tin that react, right? And so I'm going to try an alternate pattern. And so this is my second guess at a pattern. My second guess is I'm going to double the copper. That kind of makes sense because we need twice as much copper. And so I'm going to double the copper 2 times. And so what I'll do here is it's going to be 2 times 0.064. And then this was 0.032. I'll leave the tin the same. Oops, was that the reactant or the product? No, that was product. And then I'll double the copper again, 2 times 0.036. And then leave the tin the same, which is 0.068. Let's see what we get here. Actually, I know this much algebra, that the 2's are going to cancel and I get the same answer. That's not going to work, unfortunately. Well, it's worth a try. So we need to try something else. Can you think of some other mathematical equation that we can try? We could square the copper. But why do we square the copper? It doesn't quite make sense from the stoichiometric equation, does it? But it doesn't matter because we're just trying to come up with any mathematical pattern that works, and we're getting very desperate. We're getting very desperate because, you know, we're running out of time. Like, we don't want to be there forever. So let's say you're a graduate student. You don't want to be there. I mean, when I was at UCSB, there were some graduate students there that were there for 15 years. But they were in different departments. Like they had to support themselves through school. So it makes sense that they were there for 15 years. You know, because they had to get jobs outside of school. Whereas in the sciences, they pay you to go to school. So it's kind of nice. You don't have to worry about that, and they cover your tuition too. So that's a very good thing about graduate school. But at some graduate schools, like University of Illinois, if you're not out of there in 4 years, they kick you out. You know, they don't want you to take too much time. So we're kind of getting desperate, and so we just got to try different things. So what we're going to do is we're going to try squaring it. Why not? I mean, nothing else has worked so far. So we're going to square that. And we know it's a 2-to-1 ratio, so we'll just do 0.032, and we'll raise this to the first power. And then we're going to do 0.036. We're going to square that, and then 0.068 to the first. And let's see what that gives us. So 0.064 squared times 0.032 divided by 0.036 squared divided by 0.068. It gives us 1.487. This is experiment 1. Are we out of time? Almost? One more minute? So at least we could do experiment 2. Let's try experiment 2. And so experiment 2, I'm going to just square the first number here. So I'm not going to write it out, just to do it quickly. So it's going to be 0.0433 squared times 0.0717 divided by 0.0567 squared divided by 0.0283. 1.477. So experiment 2 came out to 1.477. Does this look like the beginnings of maybe some pattern? Yeah. I mean, of course there are going to be random errors and fluctuations in the data, but it looks like it's around 1.48, 1.49. But we're out of time now, so we'll look at experiment 3 next, and hopefully experiment 3 comes out close. If experiment 3 comes out close, then maybe we have a winning pattern here. If we have a winning pattern, then that's good, because then we can use that pattern to make predictions. Yes. Yeah, lab data. We'll talk about the formatting of that later, so you don't have to prepare it yet. Yeah.
Take notes and like the one that happened to
Yeah.
me. Do you want me to get like a separate book just for the lab stuff, or it is like alongside the notes? Is that
You could do it either way. You could do it alongside the notes or separate lab, but up to you. Except the lab data for the observations has to be done in ink.
okay? But just like we're not turning.
But your notes could be.
We're not turning the notes into like 1 3.
You are going to turn it. I need to just see the data, but this is a quick look at the data just to make sure it's recorded, and that's it. Right. So you could do it in there and just show it. The other thing for the lab notebook is usually we have a table of contents, so that means having to number the page so you can quickly find the experiment. But it's up to you.
Yes, because I want to pick up my ravioli.
Unless you get utensils, if not, I